Yes, I think it's a good idea.
Yeah. So welcome everybody. This is a new webinar from a RIANA series of webinars dedicated um, to all the RIANA-project participants and not only. I am Nicu Scărișoreanu, and it is my pleasure to present to you Jakub, Jakub Jagielski, which is coming from a NanoBioMedical Center, Adam Mickiewicz University, Poznan. So he will talk today about unveiling the nanoparticle complementary techniques for characterization of lipid liquid crystalline nanoparticles. It seems very, very interesting. So Jakub, please take the floor.
Thank you, Nico. So hello everyone. Thank you for joining today's webinar. As you could hear, my name is Jakub Jagielski. I'm a researcher at NanoBioMedical Center at Adam Mickiewicz University. And I'm also a Smart Science Cluster member within the RIANA network, representing the EUSMI network. So today I would like to talk about my main research field, about lipid liquid crystalline nanoparticles, and how do we characterize them using multiple complementary techniques. So the title is Unveiling the Nanoparticles, and by the end of the talk, I hope you will see why no single method can be used for this purpose. Okay, here's our roadmap. We'll start from the very basics. So what are lipids and how do they self-assemble into nanoparticles? Then I will give you a very brief look at applications, and we'll move to the core of the talk, which covers 4 characterization techniques: the dynamic light scattering, electrophoretic light scattering, cryogenic TEM, and small angle X-ray scattering. And I will show you results from our own network, our own work along the way, and we'll wrap up with conclusions about why a multi-technique approach is essential. So let's start with the fundamentals. We start with a single amphiphilic lipid molecule in water environment. The molecule consists of 2 distinct regions: a polar hydrophilic head group, which interacts with the water through hydrogen bonding and electrostatic interaction, and non-polar hydrophobic tail, which is thermodynamically incompatible with water. So this amphiphilic character creates a fundamental thermodynamic tension. The head group is solvated by water, while the tail disrupts the hydrogen bonding network of the surrounding solvent, increasing the system's free energy. This interaction provides the driving force for self-assembly. The molecules spontaneously organize to minimize the contact between hydrocarbon chains and water. How can we predict which mesophases a given lipid will form? There are plenty of factors such as pH, such as temperature, such as ionic strength. Here, I would like to show you how the molecular geometry, quantified by the critical packing parameter, affects the mesophases. So here you can see the CPP, critical packing parameter, is defined as the ratio of the hydrophobic tail volume to the product of the effective head group area and the critical chain length. Essentially, CPP captures the effective geometric shape of the molecule. So just to show you which each of these parameters is described, here you can see the hydrophilic head group. This is the hydrophobic tail length, and shaded in red you can see what is the volume of the hydrophobic region. When CPP is approximately 1, the molecule is effectively cylindrical, so the spontaneous curvature is near 0, and we obtain flat bilayers similar to those found in biological cell membranes. When CPP exceeds 1, the molecule has an inverted cone geometry with relatively small head group and large hydrophobic volume, favoring negative interfacial curvature, what leads to the inverted hexagonal phases. in the range of a 1/3 to 1.5 CPP, we obtain cylindrical micelles with the positive curvature. For my nanoparticles systems, the most relevant regime is critical packing parameter above and equal 1, where the bicontinuous cubic and inverted hexagonal phases form. These are the internal architectures of the cubosomes and hexosomes, respectively. And now let me show you how, in simplified way, the geometry actually affects the self-assembly. So when we stack our lipids one by one, they create such structure. When we substitute with this with lipids, you can see the hexagonal, two-dimensional hexagonal symmetry cross-section with hexagonal unit cells outline. So you can see that each water channel is surrounded by a ring of the lipid head groups pointing inwards with the tails extending outwards. However, this is we call bulk structure. Of course, these are applicable for biomedical applications. However, in my work, I want to use nanoparticles. So to produce the colloidal nanoparticle dispersion from this bulk structure, we need to fragment this bulk mesophase. Here we see an ultrasonic probe being inserted into the sample, and using the high energy acoustic cavitations, mainly its homogenization using the ultrasound, we can disrupt the bulk structure into the nanometer scale fragments. As a result, we obtain the colloidal dispersion of lipid liquid crystalline nanoparticles in water environment. Each nanoparticle retains the internal liquid crystalline order of the parent mesophase, but now at the nanoscale. Kinetically, these nanoparticles are stabilized by surfactant corona. Typically, we use the 3-block copolymer covalent pluronic F127. You can also observe here in this schematic that these nanoparticles are polydispersed. So we have different sizes, not just one defined specific size. Now the central question becomes, how do we comprehensively characterize these nanoparticles? So their size, their surface properties, morphology, or internal structure. But before this, let's see why we should care about these characteristics. So why do we study lipid liquid crystalline nanoparticles? There are plenty of features, characteristics, which are worth highlighting. Firstly, the lipids they are made from the nanoparticles, so basically glycerol monoolate, but also, for example, phytantrol, are generally recognized as biocompatible and safe, which is a crucial starting point for any biomedical application. Second, the bicontinuous cubic structure, which is so, well, here we have seen the hexagonal, but we, as I told you, we also studied this bicontinuous cubic structure. They contain both hydrophilic water channels and hydrophobic lipid regions coexisting within the same nanoparticle. This means that we are able to load both hydrophilic and hydrophobic agents into our nanoparticles, which is not very simple, for example, in liposomes and solid lipid nanoparticles. Third, the internal nanostructure creates a huge internal surface area, which translates into sustained drug release. The drug has to navigate through the network of channels before it escapes, giving us a natural slow release mechanism for example, anti-cancer drugs. The fourth, these liquid crystalline phases can undergo phase transitions, which we can somehow controlled, for example, by controlling the temperature, the pH, which opens the door to stimuli-responsive, controllable drug release. So as you can see, these advantages are reflected in the literature. As you can see, we already research different branches of liquid crystalline nanoparticles applications, starting from antibacterial liquid crystalline nanoparticles, which are my main research field. But as you can see, our group are also work on, for example, applications of liquid crystalline nanoparticles as a potential new type of high molecular weight contrast agents. Nanoparticles can be liquid crystalline nanoparticles can be used also as a drug delivery systems, for example, for glioblastoma therapy. But the range of the applications extends further. We have the cubosomes for topical delivery of the antimicrobial peptides. In this case, we can research theranostic drug-loaded cubosomes combining diagnostic imaging, therapeutic efficacy agents against cancer cells, and, for example, sustained release formulations based on liquid crystals for controlled delivery of bile salt derivatives. Across all of these examples, a common principle emerges. The internal nanostructure directly determines the functional performance of the carrier, which is precisely why rigorous structural characterization is indispensable. So consider the nanoparticles as a sealed container. Here you can see the grade with question mark. After synthesis, we have a turbid colloidal dispersion in a vial, but the fundamental physical-chemical properties remain unknown. We don't know the hydrodynamic diameter, we don't know the surface charge, as well as particle morphology or its internal symmetry. Each of the four techniques we'll discuss address a different subset of these questions. So let's start with the dynamic light scattering. Here is a schematic of the typical DLS setup in backscattering geometry. Specifically, here you can see 173 degrees. The laser beam passes through the attenuator that adjusts intensity based on the sample concentration, then through a focusing lens into the cuvette containing our nanoparticles dispersion. The key is the detector positioned at 170 degrees, which is almost directly backscattered light. This geometry has advantages for concentrated or turbid samples because the light path through the sample is shorter, reducing the multiple scattering artifacts. In the end, the detected signal is processed by a digital correlator, which computes the intensity autocorrelation function, the central quantity from which particle size is extracted. But what are we actually measuring? So the foundation of the DLS is Brownian motions, the diffusion of the particles suspended in a fluid. This motion arises from the thermal fluctuations of the solvent molecules, which continuously collide with the nanoparticle from all directions. At any given moment, these molecular impacts do not perfectly cancel, resulting in a net random force and a random displacement. So basically, a smaller particle has lower friction coefficient and responds more strongly to each thermal impulse, exhibiting a higher translational diffusion coefficient, which you can see in the bottom. Large particles, conversely, experience greater viscous drag and diffuse more slowly. This contrast is visible on the top part of the image. So the large nanoparticles undergo smaller displacement. So how do we detect this motion optically? When a coherent laser beam illuminates the nanoparticles suspension, each particle acts as a scattering center. And the scattered waves interfere to produce so-called speckle pattern visible on the right. Because the particles are continuously changing their positions, the speckle patterns fluctuates in time. Rapidly diffusing small particles produce fast intensity fluctuations, while slowly diffusing large particles produce a more gradually evolving pattern. Quantifying the intensity fluctuations yields the translational diffusion coefficient, and through the Stokes-Einstein equation, we can obtain the hydrodynamic radius. And I'm aware it can look a little bit intimidating, but I just wanted to walk you through how we get from the speckle fluctuations, how do we get to the particle size. The tool we use in the is the autocorrelation function. So in the simple terms, autocorrelation quantifies how similar scattered intensity signal is to itself after a certain delay, which we call the lag time tau. At a very short lag times, the particles have barely moved and the speckle pattern is almost unchanged. And the autocorrelation is high. As the tau, so the lag time increases, particle diffuses to new positions, this speckle pattern loses its resemblance to the original and the autocorrelation decays towards zero. For the monodispersed sample, which you can see in the plot as a black and green line, so for a monodispersed sample, this decay follows a single exponential, which, let me just turn on. Yeah, here you can see e to the power of minus gamma tau, where gamma is the decay rate. When we integrate this autocorrelation function, so basically this simple equation, we can obtain the correlation time, which relates to the decay rate as you can see here. So gamma is 1 over tau, 1 over tau. So the correlation time is simply the reciprocal of the decay rate. And the correlation time is the parameter which we actually extract from the measurement. Now, to make this data physically meaningful, we need to connect it to the diffusion coefficient D. The decay rate relates to the translation of diffusion coefficient D through the scattering vector, which you can see here. But basically, we can calculate that our diffusion coefficient is 1 over scattering vector squared times correlation time. Then we can simply substitute it in a Stokes-Einstein equation to obtain the hydrodynamic radius. However, in a polydispersed sample, which is the realistic case for most nanoparticles dispersion, the autocorrelation function is no longer a single exponential. Instead, it is a superposition of exponentials, which each corresponding to a different particle size with its own correlation time. The result visible in the plot on the right as the dashed red curve is a stretch decay profile. By deconvolving this multi-exponential into its components, we obtain the actual distribution of hydrodynamic diameters. Before we move to the results, I would like to tell you about the electrophoretic light scattering. While the setup is very similar to DLS, and these two features are measured very often simultaneously or one by one in the same equipment. So here you can see that before the focusing lens, we have the beam splitter that divides our laser into two paths. One goes through the sample as before, and the other serves as a reference beam. The sample cuvette is now an electrophoretic cell with electrodes that can apply an electric field across the dispersion, and we introduce this so-called electrophoretic movement of our nanoparticles depending on their surface charge. The key difference from DLS is that here we use so-called the heterodyne detection. The scattered wave differs from the reference beam by a little change in frequency, which we are not able to detect because of the technology we have. However, using so-called heterodyne detection, we make it possible. But before we go further, I just wanted to show you why surface charge is relevant. So these animations illustrated this principle. On the left, a particle with low absolute zeta potential exhibits a very low electrophoretic displacement under the applied electric field. On the right, a particle with high absolute zeta potential undergoes rapid directed migration towards the oppositely charged electrode. Higher absolute values of zeta potential correlate with enhanced colloidal stability, as the electrostatic double layer repulsion between particles provides a sufficient energy barrier against aggregation. So now moving to how the heterodyne detection works. As you can see, we have the reference beam shown in blue. It maintains a fixed known frequency. The scattered beam in red is a Doppler shifted due to the direct motion of the particles in the electric field. When these two beams are superimposed at the detector, the resulting interference signal, shown in green, oscillates at the beat frequency, which equals to the Doppler shift. This heterodyne detection scheme provides the significant higher sensitivity to a small frequency shifts compared to homodyne methods. So as I told you, the scattered beam is shifted in frequency very slightly, which is not possible to detect by common methods, but by superimposing them, we obtain this beat wave, which we can extract this Doppler shift, which then is used to derive zeta potential. So the derivation process proceeds as follows. It's very easy, I think. The Doppler shift is the difference between the scattered and reference frequencies. From this frequency shift, the particle velocity is calculated. And then, since the electrophoretic velocity is proportional to the applied electric field strength through the electrophoretic mobility, we obtain that mu equals velocity over electric field. This electrophoretic mobility is the primary experimental observable quantifying the particle's velocity response per unit applied field. Next, to convert electrophoretic mobility into zeta potential, we use Henry's equations, which one compound is so-called Henry's function, which is very tedious to calculate. So in real life, we use the approximation based on, for example, for two limiting cases. For large key A, we use the Smoluchowski limit, and for small key A, we use so-called Haeckel approximation. For our nanoparticles, we basically use Smoluchowski approximation, And then we can simply obtain zeta potential as the function of the viscosity of our sample, which is close to water viscosity, over the dielectric constant using the electrophoretic mobility we extracted in the previous slide. And here are the results from our earlier work on phytantral and glycerol monoolate based lipid liquid crystalline nanoparticles. The table presents 4 formulations with their intensity, weight, hydrodynamic diameters, polydispersity indices, and the zeta potentials. As you can see, hydrodynamic diameters range from approximately 197 to 243 nanometers, consistent with the expected size range for lipid liquid crystalline nanoparticles prepared by ultrasonication. PDA, so polydispersity indices values, remains below 0.5, confirming the monomodal size distribution, especially for the phytantral based formulations, where the PDA is approximately 0.5 and 1, which you can also see on this plot here, where for GMO 2%, the distribution is very broad and wide. Zeta potentials are uniformly negative, spanning from -15 to -24 microvolts, which also is consistent with the anionic character of pluronic stabilizer. Another results, more recent work. Here you can see how we employed a central composite design to optimize the formulation of the antibacterial lipid liquid crystalline nanoparticles based on glycerol monolaurate and glycerol monoolate, and pluronic, again, F127 as the steric stabilizer. So the response surface models indicate that a pluronic mass is a dominant factor controlling hydrodynamic diameter, polydispersity, which seems obvious, while the greater amount of the surfactant disrupts our nanoparticles into smaller and smaller fragments. Notably, zeta potential remained essentially invariant at -27 microvolts across the entire design space. So after applying the DLS and electrophoretic light scattering, we have determined the hydrodynamic size distribution, the surface charge of our nanoparticles. However, these techniques provide no information about particle morphology or internal crystallographic structures. To access those properties, we require fundamentally different experimental approach, and now we can move to the cryogenic transmission electron microscopy. For our nanoparticles, water is an unavoidable compound to remain their structure. However, due to the vacuum in the TEM chamber, it's impossible to insert sample in its native state, because the water would evaporate instantly, leading to the nanoparticle structure collapse. This is why the procedure includes sample freezing. However, we cannot simply freeze our sample. During the slow freezing allows nucleation and growth of the crystalline ice, which introduces artifacts and, what's more important, disrupts the native structure, as you can see in this picture, it's the animation. Therefore, we use a process called vitrification, so rapid cooling. Thanks to it, we get rid of the all ice crystallization and we trap the aqueous phase in an amorphous glassy state that preserves the in-solution structure. This is accomplished by simple plunge freezing the specimen grid into the liquid Ethian, approximately minus 180 degrees Celsius. Here, just to show you how this very simple equipment looks like. On the right, you can see the cryo plunge. So it's basically after blotting the excessive water from our sample, it plunges our grid into the liquid Ethian. Then we transfer it to the cryo-TM holder, which maintain the negative 170 degrees Celsius temperature throughout whole imaging. In transmission electron microscopy, image contrast can arise through several distinct mechanisms. The first is the mass thickness contrast, where electrons undergo elastic scattering from atomic nuclei, and the scattering cross-section depends on a local mass density, specimen thickness, and the most important, atomic number. An objective aperture in the back focal plane blocks the scattered electrons, so thicker, denser, and regions with the higher atomic number transmit fewer electrons and appear darker in our image. However, this contrast mechanism is inherently weak for liquid crystalline nanoparticles because they are composed mainly of low atomic number elements such as carbon, hydrogen, oxygen, embedded in the vitrified water of comparable electron density. So the resulting mass thickness contrast is insufficient for reliable imaging, and therefore it is very weak for our nanoparticles. Next, we have a diffraction contrast, which dominates imaging of crystalline material like metals, but it is also unfortunately weak for our systems. This mechanism relies on a coherent scattering from the crystal plane, satisfying the Bragg conditions, but the liquid crystalline order in lipid liquid crystalline nanoparticles has periodicities of several nanometers, far from large to produce strong diffraction contrast at typical TM operating conditions. So again, it is weak for lipid liquid crystalline nanoparticles. The contrast mechanism that is operative for our system is so-called phased contrast. So electrons transmit through the specimen, acquire a small phase shift proportional to their projected inner potential. By intentionally defocusing the objective lens, these phase shifts are converted into measurable intensity modulations through interference between the unscattered beam and the weakly scattered beams. So the phase contrast mechanism governed by the contrast transfer function is the dominant source of the image contrast in cryo-TM of unsustained, because we do not want to introduce high atomic number stains which can disrupt our structure of our nanoparticles. So yes, sorry, I lost. So it enables visualization of the periodic lipid water architecture within our nanoparticles, despite the minimal electron density differences between the two phases. Here you can see the micrographs of our lipid liquid crystalline nanoparticles showing the internal periodic structure. The yellow boxes indicate regions of the interest where the liquid crystalline lattice are pretty clearly resolved. Then we can use the fast Fourier transformation on these selected regions to reveal discrete diffraction spots corresponding to the real space periodicity. And by inverse fast Fourier transformation, we can reconstruct it around the principal Bragg reflections to isolate the periodic component from the background noise, clearly resolving the lattice. So here I just wanted to show you that these nanoparticles indeed shows this periodic internal structure. Some of them you can see even has this cubic structure, cubic form. But what is also important, as I told you before, these dispersions are not monodisperse. They are heterogeneous. So we have both liquid crystalline nanoparticles, but also a lot of different structures such as liposomes and some intermediate structures. With cryo-TEM, we have now added the direct morphological information to our nanoparticles dispersion. So we have particle shape, internal structure, and preliminary phase assignment from fast Fourier transform analysis. However, cryo-TEM provides the local information from a limited number of particles, and definitive statistically representative phase identification requires a reciprocal space technique probing the bulk sample. So the fourth and the final technique is a small X-ray scattering. Here's the SACS setup. An X-ray source, either a lab source or a synchrotron, produces a beam that passes through a monochromator and collimation slits before hitting the sample in a capillary or thin cell. The transmitted beam is caught by a beam stop, while the scattered X-ray fan out at small angles and hit a two-dimensional area detector. The 2D pattern is azimutally integrated to produce a one-dimensional scattering curve of intensity versus the scattering vector Q. So the position of the peak in this curve directly encode the symmetry and lattice parameters of the internal nanostructure. So now let me just shortly introduce the central quantity in any scattering experiment. The scattering vector Q. When the X-ray scatters of the sample, there is a momentum transfer and scattering vector captures this. So we can see that Q vector is the scattered vector minus incident vector. So this is the difference. You can see this construction in the upper and here part of this slide. In SACS, we deal with the elastic scattering. So the X-ray energy is conserved. So the incident and scattered wave vectors have the same magnitude, which equals to 2 pi over lambda. From the geometry of this triangle, one can derive that scattering vector Q equals 4 pi sinus theta, which is this angle, scattering angle, over lambda. But what does Q actually tell us? It acts as an inverse length scale. Each Q vector, scattering vector value, probes the structures with a characteristic spacing d, which equals to 2 pi over Q. Small q means small angles, which means large real space periodicities. In SACS, we typically work in the range of about 5,000 to 5 nanometers in inverse space, probing structures from roughly 1 to 100 nanometers, exactly where the internal lattice of our liquid crystalline nanoparticle sits. So the Ewald sphere here, you can see construction on the lower part of the slide, but puts this into a reciprocal space picture. The sphere has a radius of 2 pi over lambda, and the Bragg peak appears whenever the sphere surface intersects with a reciprocal lattice point on the sample. Because our liquid crystalline lattice parameters are large, on the order of nanometers, the reciprocal lattice points are closely spaced and sit near the origin. Here I just wanted to show you the animation I prepared, but I need to change how I share you my screen. Yeah, so I think you should be able to see it. We can approximate the small angular X-ray scattering experiment to Bragg diffraction. So here you can see we have the incident beam at any certain angle, and then we can scan the scattered angles. Here we have from the almost 1 degree to 10 degrees. And in figure 2, here you can see the waves. Oh my God, sorry. I need to just wipe my forehead. Okay, so you can see that at certain angles, our resultant interfering wave is a really constructive interference. This is valid when our momentum. Oh my God, I'm sorry. I confused everything here. So perhaps it will be better. I will go back to my presentation, and then if someone is interested, I can show it
No problem,
later.
Jakub. You just
Thank you. I will just go back to this. Yeah. Let me just. Okay. The results. So before we look at the data, let me explain you just how SACs allow us to identify specific liquid crystalline phases. So the key lies in the position of the Bragg peaks. For any periodic structure, the peaks appear at the scattering vector values, Q values, that are integer multiples of 2 pi over A, where A is the lattice parameter. So for the lamellar phases, the structure is simple. It's a stack of bilayers, and peaks fall at equally spaced Q values in ratios 1 to 2 to 3 to 4. For the inverted hexagonal phase with the two-dimensional array of water cylinders, the characteristic ratios are like 1 to square root of 3 to 2 to square root of 7. Which reflects hexagonal lattice geometry. Then we have the continuous cubic phases, which are most relevant for cubosons, but also the most difficult to establish from the SACS data, because we have geroid cubic phases, double diamond cubic phases, and the primitive cubic phases, each one with the specific fingerprint of peaks. So in practice, identifying a phase means measuring peak positions, computing the ratios, and then matching them against these known sequences. Now looking at our data here, you can see this is the most recent paper. Panel A shows the baseline corrected scattering curve at the room temperature, with the Bragg peaks indexed as square root of 2, square root of 3, 4, and 7, which corresponds to the double diamond bicontinuous cubic phase. From the SACS data, we can also calculate more features, more characteristics, such as, for example, water channel radius. Here you can see it's calculated to 2 nanometers. and also a water volume fraction, so the amount of water included in our lipid liquid crystalline nanoparticles. In panel B, you can see the same data before baseline correction. In panel C, you can see also the scattering Sachs profile in the range of the temperatures from 20 to 70 degrees Celsius, in which you can see the peak shifts to higher Q values and change in relative intensity, reflecting structural reorganization of the lipid mesophases. And also for each temperature, for each Sachs scattering curve, we quantified changes in lattice parameter and water channels and the water volume fractions. And you can see that in a range between 25 and 35 degrees Celsius, there is a pronounced transition region where the structural reorganization is most rapid, potentially reflecting a change in the chain melting state or phase boundary. So now with Sachs providing definitive phase identification and quantitative lattice parameters, the characterization picture is now complete. We have the hydrodynamic size, the polydispersity, both from DLS. We have the surface charge from ELS, real space morphology from cryo-TEM, and crystallographic symmetry from Sachs experiment. And this is the central message of this presentation. So we have a one particle system. We need 4 techniques and 4 complementary types of information. So DLS provided us with the hydrodynamic size and polydispersity. ELS yields the zeta potential essential for predicting colloidal stability and understanding the electrostatic interactions with biological membranes. Cryo-TEM reveals the morphology of the nanoparticles, so the actual particle size and internal texture of the individual particle level. And in the end, we have the Sachs, which provides the phase identity in a more statistically significant level. As you can see, no single technique provides a complete characterization. We need all of them. Of course, we can employ a lot of different techniques, but in my opinion, these 4 are essential for to start the research on lipid liquid crystalline nanoparticles. So if any of these resonates with your research, I want to highlight that all of these techniques, DLS, ELS, cryo-TEM, and Sachs, are available through RIANA network, not only in a EUSP network infrastructure, but of course we have all of them. Access is free through transnational access open calls available to both academic and industrial users. And if you are interested in applying or need help with proposal, please do not hesitate. You can reach me out, and hopefully face to face I will give you and provide you more information. In the end, I just wanted to acknowledge and to thank all people I work with on lipid liquid crystalline nanoparticles, and of course Roxana Mickiewicz, who is in RIANA my supervisor and my senior scientist. So thank you. And if you have any questions, I will be happy to answer them. Thank you.
Thank you very much, Jakub, for a very, very interesting talk, very interesting presentation, and very, very complicated material and nanoparticle. So please, if you have any questions. I know that I have one. I have to admit that is something which is really, really complicated to analyze and to investigate. These lipid liquid crystalline nanoparticles. uh, yeah, this you have shown us properly. But I remember that I read an article of coming from your center some years ago, related with the possibility and the use of these liquid crystalline nanoparticles as carriers for manganese oxide, if I remember correctly. It was a very nice paper in my opinion, with an application in magnetic resonance imaging.
Yes.
So for me, it's incredible how much is the payload and the capabilities for drug delivery of such of these materials. So maybe you can comment on this related to this kind of oxides and also in the terms of carriers.
Well, as I mentioned before, one of the greatest advantage of lipid liquid crystalline nanoparticles is their complex internal structure. So, for example, in liposomes, we have simply the membrane and the internal part is the water. So we can load liposomes with as much agents as we have the water inside and only the hydrophilic agents. Here we increase the internal structure and the loading capacity by introducing these two non-intervening water channels. Well, we can get the surface area up to 400 meters squared per gram of our, let's say, bulk structure of the liquid crystalline nanoparticles. So this is the main cause why the loading capacity is so high. Another thing is what I also mentioned is that we have both hydrophilic and hydrophobic regions. On the interface, we have amphiphilic regions, so we can modulate our loading agents to increase their loading capability. So we can load both hydrophilic, hydrophobic simultaneously. We can also load the amphiphilic agents, and we can modulate them in such way to increase even more this capability.
Yeah, another question is for me is coming from me is related to the statistics in terms of stability in aqueous solutions. I mean, how stable they are. For example, if you want to use it in
Mhm.
this kind of personalized medicine and drug delivery, what is about the statistics in this
Okay,
field?
well, it's very broad problem and challenge, the stability, because we mainly work in vitro scale. And when we try to measure the stability of our nanoparticles, like sitting in the fridge, they can be stable for a month, for a 3 months with no problem. The stability in vivo is completely different game and a completely different challenge because the blood environment is very complex. We have a lot of proteins. We have
No, Jakub, I'm not talking about in vivo experiments or something in vivo
okay.
work, just in vitro,
So
just
in
for
vitro,
your regular experiments.
so for in vitro, they are very stable because liquid crystalline state is natural for these nanoparticles. When we adjust the surface chemistry using, for example, the pluronic or other surfactants to gain the absolute to gain the negative or positive, but high absolute values of the zeta potential, uh, these are very stable in time. As I said, even over 3 months, it's not a problem. And of course, we have we can get the precipitation of manganese oxide, but the oxides which are already inside our nanoparticles remain stable.
Okay. Okay, so if there are other questions, please. Okay, if not, I have another one. How do you intend to proceed forward, Jakub, in your research on this topic? I mean, only antibacterial
Well,
applications or
our
antibacterial
group,
application?
our group study uh, studies different branches. My personal part is the antibacterial part, but it's not like loading the antibiotics inside the lipid liquid crystalline nanoparticles. But I tried to modify glycerol monoolate lipid liquid crystalline nanoparticles with the bioactive bioactive lipids to gain new features, especially bacterial membrane disruptive characteristics to obtain the system which can breach antimicrobial resistance. So my idea is to use nanoparticles as a carrier of bioactive lipid, which leads to specific disruption of bacterial membrane, impairing the functionality of the efflux pump, and simultaneously to deliver antibiotics, which becomes active due to the impairment of the efflux pump. So uh, we can reuse antibiotics which became non-effective for bacteria which gain resistance to them.
Jakub, this is a very, very interesting topic, actually. So, other questions? If not, I wish to thank Jakub one more time. It was a very nice talk and very nice subject, and all of you for for your presence and for support with on these webinar actions within the RIANA project. So see you next time, guys. Have a nice day and all the best.
Thank you.